yesterday, 2019, I received this nice invitation by DM, and I found the name of the festival real cool, Festival de Théorie. That sounded wonderful. Of course, I couldn't come because of some earlier commitments, and I'd forgotten about it. And then when I received the new invitation by DM, it was 6 months ago. Well, of course, I was happy to come because, like all of you, we have been sort of stuck home and talking to our computers for a couple of years. So it was actually very nice to be with you. Well, I understand that, for friends in the US, or even further from Asia, it's still a little bit a long way, but at least there's some kind of progress, and it's wonderful. So what I will be telling you about is some work, it's some sort of a summary of works that we've been doing. The origin of that work actually goes back to my postdoc, long ago, I had no gray hair at the time. So it's something that has, it was about the search for singular solution from the Navier-Stokes equation or Euler equation, whatever you can do, which was a problem for which we sort of had, we ran into difficulties. And having that, I said, well, look, I was not too thrilled to go back to it. It took Michael Brenner, with whom I had many discussions, to bring me back to the problem. We revisited, and I think what makes the thing, in my view, most interesting was that there were some experiments that we could propose about some ideas. Not that they solve everything, but at least sort of lead to some progress. So Michael Brenner was the person who, like I said, got me back to that. At the time, there was a postdoc actually, Sahano Moz, who sort of left now, and he is in Harvard Medical School. So people sort of made a huge, he made experiments at Shmuel Rubenstein, now at the Hebrew University, and Ryan McKeown, who was a student back at Harvard. And I've been working with it with Rodolfo Stelamonico, who was then postdoc at Harvard and now in Spain in Cadiz. Okay. Okay, and that one should go. Yeah. Okay. So so I sort of mumbled something about large gradients and possibly singular solutions. Why should we care at all? So let me sort of go back to the beginning, following the guidelines that were sort of given by the company. So we're looking at large Reynolds number flows, and the large Reynolds number we learned in fluid mechanics early on 101 or something. So the Reynolds number is just the ratio between the convective term here and the dissipative term. Okay, so we say that's large, and so if that's large, that effectively means that the dissipation term potentially is small. Okay, wonderful. So that would be fantastic. So we have a flow and there'll be no dissipation. Is it that simple? Well, no, of course not. And the observation is that, in fact, that dissipation, so if you look at how much energy is being dissipated per unit mass, etc., so you have to calculate this object, which you reduce, up to boundary terms, that thing here. And what you discover is that everything is finite. So effectively, you have this mu, which is potentially small, but the gradient Q square effectively makes up for the small mu, and you have a finite energy dissipation. So that's something which is called the dissipative anomaly. So there is always, in spite formally viscosity can be very small, there's always some finite dissipation in the flow. which means that, there has to be some strong velocity gradient. And the underlying question is how does that happen? What makes the flow generate these large velocity gradients, which effectively will produce for you some finite energy dissipation? So that's a very old question, and people who sort of are pioneers in this field. So here I'm alluding to G.I. Taylor. Asked himself the question, and of course he had in mind turbulence, but he sort of came up to say, well, let's sort of do something much simpler. And Lorentz has something which is as simple as it can possibly be. So a bunch of sine and cosine, and we know that by the nonlinearity, by the time you start putting modes together, with 1, 1, 1, you'll be generating modes 2, mode 3, mode 4, mode 5, etc. And of course, you'll generate the whole thing. The question is how fast does it go, and how much, how large gradients. Because obviously, if you sort of start generating some higher harmonics, by the time you take the gradient, of course, you'll generate some big, large gradient. And so that was this sort of innocuous looking initial condition, which started, seriously, again, which Mr. Taylor, on the very student, somebody, started doing back in the 36, almost 100 years ago. And they sort of saw that the dissipation of energy was picking up as the Reynolds number was increasing. So, which of course, you have to put. There's no correlation with what I was saying, but these people ask themselves that question on a very simple floor, completely ad hoc. But then, of course, the quote-unquote real solution came a few years, in a different strain of thinking. It was sort of started by, it's attributed to Richardson, who came up with this famous little verses, big worlds of little worlds. So in other words, if you take a bucket of water or of fluid, start stirring it, so you have some big world as the size of your system. And then the thing, as it goes on, that sort of eddies will break up into smaller eddies and on and on and on. But we don't get velocity and little worlds as lesser worlds. So that's what I would say that's much less poetically than Mr. Richardson, and so on to viscosity, i.e. It goes all the way until it cannot go any further because viscosity starts kicking in and effectively stopping the process. It's not really the same thing as you obviously see. It's not the same sort of degree of accuracy as the prediction of the works that Taylor and Green were proposing to do. It is much more of a descriptive thing. However, with the input of Mr. Kolmogorov, we sort of gave as much as could be given to that one. That sort of became the, prevalent, if you wish, theory of turbulence. But still, again, having said that, there is some sort of a hiatus between that description and the fluid mechanics. When you start asking, how does this thing break up? How do you sort of do these things, etc. Number of questions. If you start asking sort of hard questions, you start fizzling because you don't quite know what you're doing, or at least things are not on very solid ground. So on one of the slides shown before, where people said you should put things which are not fully understood. So that's effectively one of the things that is not entirely understood, and which I will be trying to sort of address to some extent. So first question is what is hiding behind the simple picture of the cascade? So what's the fluid mechanics behind it? and how can we sort of relate it to anything that we know from fluid mechanics. Okay, so large gradient. So I basically told you that, well, there are large gradients because there is this sort of a law of the turbulent flows that says that effectively the viscosity drops out of the energy dissipation, even when it's very small, viscosity drops out to generate some order 1 energy dissipation. So that sort of gives you for free a large gradient. But it's actually not even, it's actually even worse, more spectacular. So in fact, large gradients, what I mean by large gradients, that in fact, even with the fact that there is some large RMS, large variance of the velocity gradients, in fact, if you start asking, comparing, looking at the fluctuation of the velocity gradients, they can even be much, much, much larger than these mean, the average value. So that's what was discovered by people that Townsend, and which is sort of summarized, for example, in this plot here. So what you have is it's a surrogate. So, it's just one component of the velocity gradient tensor, which you can measure in a turbulent flow. So a typical setup, which you possibly know, just interrupt me if it's boring to you. So you have some big flow flowing horizontally, saying the x direction. You're sticking a probe that measure ux as a function of time, and there's a flow of the things affected, and therefore you have some the notion of ux as a function of t, and then you sort of say that t and x are related by what's called the frozen hypothesis, and that allows you to sort of measure some approximation to the velocity gradient tensor. But never mind. So that's all these technicalities to say that here, that thing here has been divided by its mean, right? So the mean is here at 1. And you observe that, in fact, the signal is not gently fluctuating around 1, but it's almost all or nothing from values which are much, much smaller than 1 to these spikes, which are of the order of the dozens and even more. And the effect is not going away with the Reynolds number. If anything, it's getting worse. It's getting more pronounced with the Reynolds number. So that effect, so the spikes become higher and sparser as the Reynolds number increases. So that's some sort of experimental thing. So what we did on some other strain of research, which I will not be telling you about, not much, is that you can measure the velocity gradient in a flow divided by the mean that's effectively divided by its mean, and you sort of show as function of the Reynolds number follow like so. So, and what you observe is that this fluctuation develops these insanely large scales as the Reynolds number increases from 100 to 600. So, you get something which is like 4,000 times the mean. Well, of course, probability is not very long, but still, these things are gone. So, that's saying that effectively these velocity gradients, they have to be large on the mean, and furthermore, they have to have these very, very, very large fluctuations, which is a phenomenon. Well, it's not. Yeah, it's sort of on my second word on my title. That's called intermittency. So that's what it is. So which is sort of again asking with more insistence this question: is how does vorticity of strain grow in turbulent flow? So is there some mechanism whereby these things get amplified to reach this insanely large value? So most probably it's sort of going, in a sense, back to the question of Mr. Taylor on the green, that there must be some nonlinearity during how does it work, how does it do what we observe. Okay, so that's effectively is one sort of set of questions that we had in the back of our mind. So I'm saying again, so looking for mechanisms of velocity gradient amplification, and again, I'm sort of arguing that it's one of the fundamental ingredients of turbulence. Okay, so let me. Okay, so that's effectively setting the stage. So let me try to, hopefully I was still, as I was supposed to do, I be sufficiently general. You guys interrupt me anytime. Obviously, I'm okay. So now let me sort of, again, at some sort of a level of generality, but try to go slightly deeper. Okay, so I will, those questions, velocity gradient amplification. And I'll sort of look first, well, I'll look mostly on the case of vorticity, because that's the one that sort of looks simplest. Well, the devil is the detail, as one says, but nonetheless, I'll do this one. So if I sort of write maybe strokes for the vorticity, so you write through maybe strokes, you hit it with the curl. So you have that equation. That guy here is the advection along a Lagrangian trajectory of vorticity. So that one is pretty innocuous. So that one is effectively viscous dissipation. So again, that sort of doesn't look too bad, but just like that. And that guy here is the one that effectively can do the damage, can sort of do something. So with people typically, it's pretty obvious, pretty easy to derive under this form here. So it's a product between vorticity component and the S, where S is the string rate tensor, which is so the symmetry part of the velocity gradient. And so that term here is effectively called expression. Okay, so now, so in what I wrote, there's nothing you can argue about. That's what it is. You derive it, and new discussion. Now, so I'm going to start, doing some hand waving stuff. So dimensionally, of course, S and omega are both velocity gradients, right? So if you're sort of naive and say, well, you have two quantities which are dimensionally, well, sort of a little cousin, and they must be deeply related. So this equation, taking this two cases, that would get omega over t. Ignore that one for the time being. So you have an equation of the form d omega dt equal S omega, right? And okay, so if you're very naive, you say, well, again, S and omega are related. So you sort of see your argument is to say d omega dt equal omega squared. Just ignoring all the differences between S and omega. And then you have some trivial ODE, which you can solve, and which predicts for you that omega will diverge like 1 over t star minus t. There's just the solution right there. Okay, that would be an interesting statement, but but it's a little bit strong. And in fact, so this virtue of this little argument is that it shows you that there is a product. the solution I gave was obviously completely wrong, or rather, it's completely irrelevant for what I'm going to say. But again, just saying that if you sort of count nonlinearity and powers, you are potentially problem. So then, of course, you can do it more seriously and ask the mathematical colleague to do it for you. And then we sort of enter in the mathematics. So take maybe state, incompressible maybe state, with proper boundary condition and an initial condition that's as nice as it can get. So you sort of let your friends pick their favorite function space and sort of take their U0 there with all the regularities they need. So there are a number of questions that you can ask. Well, the first one, which is not even obvious, well, of course, it's obvious to us because we're using these equations all the time, but insofar as mathematics goes, it's not completely obvious. There doesn't exist a solution at all. Some equations are so badly posed that, in fact, there's no solution at all. And if there are solutions, do they exist for as long as you want? To the first question, the answer is yes. So that was some sort of remarkable work. So the French-speaking in the audience, that's a text which is written in French. 100 years ago, it's actually very lovely to read. Mathematics is not that, you can actually follow it. For those of you who went to cascade and all that, you have enough, and so you learn how to do these things. So you can actually follow it, and it's written in beautiful French. So well, okay. If you have nothing else to do, please go for it. It's a nice one. Actually, and there's some English translation. It's been translated side by side. So the French page, English page. So everybody can follow that one. Again, it's a beautiful paper. Do solution exist at all time? That's a really hard map, which has not been cracked yet. So I think for this talk. And that's what the K Foundation put up as one of the millennium problems or whatever like that. So it's sort of a following up on these Hilbert problem. So okay. Laura actually did more. So there is, okay, so give yourself an initial time, a U0, and then you sort of play with your Reynolds or viscosity, whatever you want. So, you just play with, with Reynolds. So what he showed was that if viscosity is strong enough, then he can solve all that. So effectively, if viscosity is very, very small, is very, very large, so then you start with some Stokes-like kind of problems, and the rest is some small perturbation, and you can effectively control the weakness of the perturbation, and then everything's good. That's low Reynolds number. And if you sort of push it in Reynolds number, you can still, so then of course you lose the possibility to show that the thing sort of will work at all times. It still can work for a finite amount of time, over order 1 or something, and then doesn't know what to do. So there is some sort of a bound above which it's sort of hard to there's some rainbow. It's hard to get past the rainbow. So that's the thing. Okay, I'll just to comment on that because obviously Leray was in 1934. And of course, people have not been sitting still and waiting for the thing to sort of clarify itself. Our colleagues are working their mind. Okay, yeah. So I think sort of you'd have to go here. So so here I'm just sort of extracting from the literature a couple of results for the purpose of this presentation. Okay, so. And again, for all of us who've done some mathematics when we were kids, We all know that sometimes our mathematical teachers were coming up with some completely insane solution of some completely contrived, and there was some counterexample of something else. We say, well, fine, who cares about that? Well, okay, not so for this problem. In fact, if there is a lack of regularity, that is for good reason. And the good reason is that if the flow becomes singular at the time, so Loret proved that if he loses, at least one of the relation between loss of regularity and some time star, had to be with the condition that the max over a ball of this u of xc had to be larger than a times greater than b times t star minus t. So in other words, if the radius torque starts going up, then you have a velocity that has to blow up at your face like this, which is pretty strong. That's exactly what I was trying to say. You could have imagined that a singularity could have been derivative 278 goes bad and all the rest is fine. In which case you say, well, I don't care. That's precisely saying that no, that's not what's happening. So if something happened, that's something big. Okay. And of course, it's so big that it's saying that the velocity gets larger than the sound velocity, and then of course your maybe fixed model gets kaput. So it's just just for it to crash and do something like you have to compressible flow, etc. But that's if there is anything happening, that's something big. Surprisingly, then in the same vein, there is the case of the Euler equation. So you in the Loret theory was playing a very special role because as I was hinting in answering the question, you effectively start with the solutions that you know that you control, which is Stokes, and then you expand. So of course, not quite the case when mu equals 0, i.e. the flow is implicit. So then you don't have this condition for u, but what you have with sort of the Kavanaugh criterion is that you effectively have a bound on the norm of the gradients by the initial values than this quantity here. So and that so in order to have that guy to be very large again, no matter how large the scale, K can be my favorite 397 derivative. Well, no, if it goes down, it means that that guy went back. That guy went back, so it means that the vorticity, the subvorticity, is effectively becoming very large. So again, one or the other, you have to, you're dealing with quantities which have mean, again, not some insanely large velocity derivative, which no one would ever care about or notice in any experiment or numerical simulation. Okay, so that's what, yeah, that's, yeah. Well, I'm sorry, that's, that is, that's the integral of the space. Yes, and yes. Right, that's right, yes. Right, when using integral is x. Okay, yeah. Okay, and then of course that's been refined. So now I took that one because it's sort of simple, but again, it's 84. Okay. And then, so what people have done, the whole literature in there. So people have tried to say, well, okay, let's imagine, effectively, Loret introduced this concept of ring solution. So whereby he says, well, the solution may be just what you expect, i.e. a strong solution, and at some point you have something else, and you can sort of still tame it using distribution. It's a kind of construction we use when we do distribution, i.e. weak solution. And then, so it sort of means that when the thing will go bad, there will be some particular loss of energy or something. And so that's a line of research that people have been pursuing. Namely, trying to say is that imagine that you have a solution in xt, so for the 3 plus 1, and the solution just goes bad on a few sets in x and t. And you say, well, you try to estimate how much energy you're losing each time. And so it's sort of telling you how often can these singular points happen. And, one of these is discovery from Nuremberg, effectively sort of provide a bound on the fractal set of the space and time points over which there can be singularities. So the thing cannot be very large. Okay, so that's there's a whole story here, which again I'm just scratching the surface. Again, my main concern being, I believe, like you, a physicist, a dynamicist, I'd like to see what are the implications for my real field. And these one are, I mean, maybe I don't see something else deep in mathematics, but these one are sort of the big one that you can. So, okay, how much vortex stretching can get? So, I sort of mentioned my childhood, so to say. And so at the time, one of the problems that sort of became attractive was the story. It was sort of to do two vortex truth, just so you just imagine to tornadoes of sorts. Turn out that the sort of most favorable configuration to do that kind of game was the anti-parallel. So one going up, vorticity going up, vorticity going down. So and then okay. So there's some long story. If you sort of do some very simplified model, also known as BS of R, whereby you neglect the structure of the core, well, you find that there are conceivably, there are some traces or hints for a singularity whereby there will be some infinite stretching in the finite time. Okay, which sort of led us to look at these kind of things, but now from the real Navier-Stokes equation, so real equations, whereby vortices are vortices, i.e. that-core, which is very important. So, and here, I'm sort of the two boxes on the left are sort of showing the evolution of the centroid of the solution. So it's evolution just so the two guys are just coming together. They starting far away, and they sort of develop this sort of go with each other like this. That's sort of from the front. But the sort of most important thing is this little video that I'm going to show now, which is a cut of the solution to the sort of middle thing. So the sort of guys come together, and so what you see without the slightest doubt is that effectively what's happening is that the sort of cores do not remain nice cores. So if you think of nice vortex, so I know it has a core, and this core is mostly circular, and the thing sort of does its things, but remains simple circular, and then you can do this of R and you can do the same. But that's certainly not what's happening here. So that thing is effectively the two guys are coming together and squashing each other and forming this these sheets, vortex sheets. Okay. Okay. And that sort of led us to think, and that's where, okay, that's some sort of an old story. And that's what, well, I reconnected a couple of years ago well, almost 10 years ago, with Michael Brenner. So they say, well, you know, how do you think about this interaction between anti-parallel vortices? Okay, so if I want to oversimplify the story, I'd say, well, you know, I have these two guys, plus minus, and then I let them go, and this little video I was showing, the push, it's just sort of a squash one toward the other, and it forms vortex sheets. Okay, and then vortex sheets, well, you know, that doesn't look very good, because if you have sort of vortex sheets, that sort of effectively means that the thing will be mostly two-dimensional. And some flow which is two-dimensional will effectively vortex stretching disappears. So that's not very encouraging to get any sort of amplification past that stage where the things are squashed toward each other and become vortex sheets. Yeah, so that's repeating myself. So the sort of a little crazy, well, maybe not so crazy, maybe a bit crazy things that we had in mind, say, well, you know, but maybe that's not the story. So, you know, like I was showing before, let's say, well, hey, how about before? It could be possible to have these guys effectively not stay still and do something else. And one of the things that we could possibly doing would be to effectively start rolling up or developing some instability. So here, you know, maybe it was not pretty well, it was maybe a little bit misguided, but well, you know, the obvious instability that affects the sheet is Kelvin hormones. So that's effectively, so what's happening here is that you have vortices, and but you know, never mind. So on either side, it's a shear layer, and shear layers are unstable by Kelvin hormones. And then, well, we sort of guessed, well, no, these guys will get in and will effectively regenerate some vortex tubes at a scale that is smaller, with a circulation most likely, well, which has to be smaller, but the things that can say just start again, and you could imagine some iterative scenario whereby the thing sort of does produce more and smaller scales, not all in one shot, but again through a cascade, each time assisted by some instability. So yeah, and I guess one sort of inspiration was this paper by Terry Tao, where we had some sort of a, you know, it was actually very hard to understand for us to understand what he meant from a fluid mechanics point of view. But you know, there is some sort of notion that we think we just go push one step and then redo another step, and of course this thing would be logarithmic in time and leading up possibly to singularity. Okay. So for that one, okay, I'll spare you most of the detail. So I guess suffice to say here that you can actually, it's a little slide I was showing, you can actually try to sort of put the flex on the bones and effectively do some little calculation using effectively things that you know very well and are mostly quote unquote sensible. So effectively, you sort of go and borrow from the literature regarding hormone instabilities, like 150 years ago, and the formation of vortex sheets, so there's some work back then. And effectively, so what you can write is an iteration for, so effectively, so you know, here I would characterize one set of filaments by a radius Rn after stage n and some circulation gamma n after stage. And then I sort of do something here and go back to stage n+1. And so effectively that you can describe by mapping. Sort of effectively mapping will connect the radius at stage n plus 1 to the radius at stage n, and gamma to stage n plus 1 at gamma to stage n. Of course, it's a kinetic. So gamma Rn gamma n basically the Rn plus 1 gamma n plus 1. So I think the thing is it's a little bit of a formal exercise because I don't think that's what really happening. But that thing certainly gets a solution. It has some sort of fixed point at infinity. It's sort of a 2 pence worth remark is that it's a if you iterate it out, there will be some solution at the iteration that will sort of give you some solution at infinity, some fixed point when n goes to infinity. The sort of a amusing little remark is that actually this instability, this fixed point is unstable, which is somewhat of a stern reminder that it's not because you have a solution that goes bad that it needs to be stable. So if you sort of do what we have, for numericists have been doing, sort of try to calculate and sort of see whether the solution will go to the unstable, the diverging solution, that may be difficult because this thing may be in fact unstable. Because looking at the cartoon version, it comes across more as a sort of a cycle. You have tubes, shoots, okay, absolutely. That was very much what I was trying to, say. Okay, so I could sort of spend a few more minutes on that one. Let me not do it because I think this inspiration, that sort of serves as a motivation more than anything else. Because it's wrong. It's wrong in detail. However, the notion, I'll try to sort of say is that later, that the notion, well, the detail is wrong, but the notion is still there on something which I have maybe more to say and can make it somewhat more convincing. So yeah, so bear with me. Okay, so that's effectively, your question was exactly where I wanted to go. So I sort of made up a little story, calculated something, tell you that, well, I don't want you to believe it too much, but let's look at what we should be looking at, i.e. interaction at high energy. Okay, so let's see. So okay, so I have till 10:15, 10:30 or something. Okay, but I'm going awfully slowly. So I guess I don't see anyone objecting. I don't see anyone yawning, or or you guys have to polite. If you're unhappy with me, scream or something. Otherwise, I'll continue my way on the, I will stop when it will stop. Yeah, no, but okay, good. Okay, so I was sort of I for some reason selected this problem of vortex to interaction. So there is one famous, one case where things can be studied is when you shoot rings at each other. So that was this experiment in Australia. So they obtained things which here are beautiful. So they shoot the cannons, these guys to each other, and so as they sort of get closer, you have some stability, and you get some small rings, and so there's some sort of a mathematical story here. It's at the Reynolds number which is, well, if I define the Reynolds number as a ratio between the circulation of the rings and the viscosity, that's mu is well, a good Reynolds number is a ratio between circulation and viscosity. Two guys have the same dimension. So yeah. So that's okay. And that sort of goes with all sorts of nice twists and turns. But that's what I call moderate to low Reynolds numbers. So because there's just no way you can say that it is still that's pretty low. And then they sort of in their papers they have one picture where they sort of shoot it at the higher Reynolds number, like so. So what happens is two guys come, collapse, and then effectively the thing bursts and effectively vanishes into some sort of turbulent path. Between 1,000 where things are laminar, on the 3,000 plus where the thing goes on the vanishing in thin air, there's something going on. Apparently, I don't know. So these guys sort of did it once. They couldn't do it again. So there's this sort of a nice set of pictures, but it was impossible to sort of do it again. So my collaborators, well, Shmuel and Ryan, well, we did it. So it was 30 years ago, a long time ago, so effectively, my collaborators started doing it with more high-tech kind of things. Well, so the sort of experiments is some sort of, first of all, a good control of all the cannons, so things that you effectively have a piston, which it just pushes and sort of ejects fluids, and then the thing just rolls up and gives you a vortex. So in a sense, that one is probably done better than linear methods. Of course, in fluid mechanics, the sort of big things that happened over the past 30 years was the availability of all these sort of the cameras, which some very, very fast acquisition rate, which allowed them to effectively develop some tomography thing where guys sort of do some planes one by one, very fast, and construct the flow, rather the die. So what they do, which will be obvious, okay. So that's the thing here. So you obviously see that the two guys, the two vortices have been dyed. And then effectively you can follow the dye, and you sort of follow right in the region where they're going to interact. On either side of the mid distance between the two. And you start effectively reconstructing. So that was what I was saying here. So the sort of these sort of characteristics here are effectively what they use to reconstruct the field of dye, and then from which, well, that's all we can do. So in fluid mechanics, measuring vorticity is a bit of a drag, but you can follow the dye field, which sort of gives you some idea. And actually, so what we did to sort of make sure that it was not complete trash, we actually also did experiments simulating, so looking at vorticity on one side and at the scalar field, dye field, if you wish, and sort of comparing, making sure that the thing was not too far off. So anyway, so that's effectively what I will be after. And then, so now you see that, so the thing, we are clearly on the side where the sort of guys collide and they push, disappear, and, no little cascade of, reconnection and things like that. So that one's much more violent. Okay, so let me try to sort of dissect what's going on. So, okay, so you have this sort of two rings that were going like this, So here, what I'm showing here is some second. Let's see how. So there's sort of that's sort of a ring. So now after sort of taking some section of the ring here, and there is a little one guy on one side, and there's a guy on the other side. There's a circulation indicated. And so if you sort of see what's going on, that's the evolution that you can see. Again, it's a die. You know, is it vorticity? Is it something else? It's a die. Okay. And I'll sort of again, given what we've seen, we have reasons to believe that that's indeed vorticity. So manifestly, what happened in between the two times I have shown here. Too fast. So here, these two guys are almost straight, and obviously there are corrugations which are developing on each of these vortices. And so, which you know, in good or fluid mechanical terms, is suggesting that there is indeed some instability going on. So these guys started relatively straight, and then corrugation grows. Okay, so that one is just summarizing sort of the what's happened with the little thing I showed you. So these two guys come together, and so there's the separation. So it goes down, time goes up in seconds. So that's 100 milliseconds here, and all these points are measured. So, so giving you a hint of the resolution that my colleagues have reached, and then sort of on this blue part, the perturbation breaks down. So which is roughly speaking that little diagram here. Okay, now and so yes, so okay. So what I was showing here is that please hold the fine. That's one. That's one. But if you want the short answer, yeah, there's a very solid point. I mean, very good point. So that one, current stability. Okay. No, well, no, I guess it's probably my next. Yeah, okay. Right. Okay, so you introduced it. So, okay, so we're talking about vortices, right? So, and we're talking about plus minus anti-parallel vortices. And what the situation you're alluding to is this all the classical calculation of a crow in the 1970s or something like that. That was at the time where I think the motivation was that there were all these accidents because they were trying to fly. Well, exactly. Yeah. So there was this sort of a big giant jet, sort of generating some huge vortex pairs on the they were doing crazy things. But aside from this application, there is a thing that you can see very often on the field. So sometimes you see this sort of two vortices at the following two rings, and so you see them. They sort of start very straight, and there's this condensation trace, and then after a while they sort of become unstable, and effectively, so that's where the current stability happens. So the current stability. So what is it? So it's a long wavelength stability. So it's just so if you have these sort of these two vortices with some very relatively thin vortex cores, the wavelength occurs over a distance which is much larger than the vortex cores, vortex size, and also the two. It's in the case where the distance between the two cores is pretty large compared to the core size. So it's this. So that's the tips, and the sort of things go like this. So that's sort of perturbations that grows, when the pen is gone already. And so what that thing means that it means is that together and then we can push the buttons. So that's what. And it's a very elementary calculation. So you just take this bar and you find the crank and you do it. Okay, so in fact, that thing which was supposed to go is actually showing what it is. So on the rings, under the proper condition, so you see that so it sort of develops this sort of wavelength, which is still very large compared to before, and sort of brings them like this. But then that's not the end of the story. So at the time, there's this competition between traffic and MIT. So so what was at stake was that there is this other instability, which is called the elliptical instability, and which is a much shorter wavelength, and which occurs when the cores are actually much closer. So let me okay. So so there's a thing on the right side of the screen is so take on message. Yes. Yeah. That's very much the point. That's very much the point. So that one, the cores are pretty far from each other, and effectively the cores are doing what? It's effectively as if you are doing this a lot, and the thing are sufficiently far, and not very much happen. So I guess the elliptical instability. In fact, it involves in an essential manner the internal degrees of freedom of the core. So it's not just that you can think of it as a tube, as something like this, where the degrees of freedom of the core are slave to the motion of the tube. No. So in the other case, the distribution of vorticity is actually a two-player. So the deformation of the distribution is important. So and I guess that's how I understand your question, right? So you were showing that it's not that I was having some sort of nice little filament tubes, but the thing looked a little bit more choppy for a reason. Yes. So in other words, so I guess maybe my answer was not very proper, or maybe not very accurate, but that may be one of the important separating points. So these one are you are allowed to think of the core as as this, and then the degrees of freedom of the core are not doing very much. I mean, we're doing something, but not a hell of a lot. Not so on the other case, where effectively it's a deformation of the core, which effectively is driving instability. So that's so I guess that would be sort of the most actually accurate thing to say. So I've been a little bit fuzzy here. Okay, so so that one is continuation on this current stability. So okay, that's what it is. So all right. So long story short. So effectively, one way of thinking about it. So if you have your two vortices, the two guys are moving with each other, because it's vortices are betting each other. But you sort of look at the field around them. There's effectively a strain at 45 degrees. So if you have the direction of motion, there is some strain at 45 degrees, which generated by each of the vortices, to which effectively the perturbation here line. And so doing, they also generate from the top this one here. So, I'm saying that if you look at it from the side, let's see something like this. The planes over which the vortices are forming are at, well, not exactly 5 over 4, but of the order of 5 over 4. It's just saying that effectively the strain is, the main eigen direction of strains are in the direction under the thing. So there is some slight perturbation on this 5 over 4, but it's really it's more or less 5 over 4 for each strain. Okay. Incidentally, I guess you have neighbors here who know everything about that. So Thomas Leveke and Stéphane Dizès, they sort of know all these things very, very well. So the other one is elliptic instability. Again, the other one you could get away. Mr. Crow just did some Biot-Savart calculation, by paper of some Biot-Savart calculation. So this one is actually more subtle. And effectively, so about two things. So there is this sort of there's some Kelvin modes, some sort of a rotation of the perturbation line vortex, and the sort of a strain which is acting upon the vortex. Again, it involves in an essential way deformation. So the deformation of the core is not something you can try to sort of sweep under the rug and try to sort of move on saying that you didn't know. No. You have to know this, and that's important. That's crucial to the calculation. And effectively, and so the thing goes obviously like the 1/d squared. Which of course, the closer you to vortices get, the most intense it gets. Okay, so the other two players, and again, they sort of bring two very different intuition. One of some filaments which are where the core is doing almost nothing, and the other one which is our fate of fluid dynamicists, where a core is a core, and that it has its own degree of freedom. I guess that remark comes when that people are doing helium-4 vortices. So for these people, effectively, they don't care. They don't have a core. The thing is just what makes a vortex is just some sort of order parameter that goes to 0 over a microscopic length scale of 0.1 nanometer or something, and there is no structure at all to speak about. Not so for us. So that's when people say, well, you see this one for helium-4. Why don't you see it for Euler? Hold on. You have to sort of see what the role of the core, and the role of the core here is doing everything. Okay, so that's again. So yeah, and I guess I didn't insist, but these instability tend to generate the opposite symmetry. So I was saying that the flow this way and that way, and sort of that tends to be like this from top, and like this. So it's yeah. It's not a symmetry. When I'm yeah. Okay. Okay. But if you look at it, you also know that symmetric is one thing. So that's at the stage. Because very good. I'm sort of keep up. We have calculated we also solve it, but that's different. We don't quite know that. So it is true that the algorithm, yes, we can be right. And in fact, so what I'm going to say is not based on the that's sort of what you see by the style of the pen. No doubt. Yes, there are the other one, but again, you enter into Mercury. Thank you. That's yeah. Thanks for keeping me honest. I was clearly oversimplifying. Okay, so but that's okay. So I guess that's what I was saying. So that one would be clearly of the other symmetry. So it's not what I was ready to attribute to Crow. Doesn't prove, if that's what you want to say, it doesn't prove that this is the elliptic instability. Yes, you're correct. You're quite correct. Okay, and that sort of left is experiment, right? Is simulation. Well, the values of our Reynolds are a bit different because we're doing different things. Okay, so what you can do to try to sort of be a little bit more precise, I mean, not infinitely more precise, is try to sort of ask yourself, well, do the exercise that we're doing, i.e. take two rings, adverting themselves by use of R, so their solution, it's very easy to calculate, and put on top of it an instability, ask yourself how fast do these guys grow. And, we sort of borrowed from a paper, a local paper, again, from your friends somewhere in Marseille, Stéphane Diaz. And we sort of, so what we see certainly is that, so the growth rates over time. So, what's happening is that these vortex rings come together, grow, right? So, and two things happen. So, again, so here I'm sort of I'm pretending that the sort of the core is not doing very much to me. And basically, I'm just sort of growing and stretching, and then so you can ask yourself what happens to perturbation of wavelength n originally. So, and of course, as the vortex stretches, the wavelength will of course stretch as the size of the radius. And so that's typically what you find. I guess what's important here are the values of the Reynolds that are involved. So that instability effectively requires a large value of the Reynolds number. So in this very, very small, in much smaller Reynolds number, you don't have very much. It's just saying that what we have is happening at large Reynolds number. That's effectively in the range where you start seeing these, the phenomena, some of the phenomena we'll be discussing. So that's effectively some sort of, what shall I say, some sort of indirect evidence that says that here we have effectively this elliptical instability. So the two of them, agree with you. Not 100% sure. The remark of DM, however, that the filament didn't look smooth, but was doing something funny, is actually some other evidence. And the last one will be sort of the nonlinear development, which people have looked at, and when you sort of see a number of phenomena which do not look at all like what happens for Crow. So, okay, so I'm mumbling here, I'm trying to justify myself. Not bulletproof, not waterproof, but yes, N was, I was just sort of taking, taking my ring and putting that was this as a neutral wave number along the vortex. So which corresponds to a wavelength. So and that can actually change it, which explains where you only see. So there is some sort of selected, there's a range of wave number which is unstable, and as time goes on, R increases, this wavelength increases. Yeah. Okay, let's see, what time is it? Yeah, half of. So how do we play? I mean, I can go aside from the fact that I'm probably mumbling more than usual. Look, I mean, I was about to say, well, I can finish it up this afternoon, or you prefer me to sort of actually have it be 100% for discussion. Okay, fine. Okay, good. So then let me switch and try to sort of go faster on the. Well, okay. Okay. Fine. Okay, so I'll try to wrap it up in 5-10 minutes. Okay, so I'll skip a lot of slides. No, I mean, I'm sorry. Whatever, I mean, you're the customer, right? So, okay, so I was sort of discussing before sort of elliptic instability, and then sort of effectively. So what has been done in great detail was in linear instability, right? So how the thing starts doing. Except that for us, what also matters is the sort of nonlinear development. And the nonlinear development is effectively, okay, so I'm correlating here with some other people within some numerics on putting sort of the two things, two tubes, where they sort of know that the beginning of the instability is elliptical, and then the thing sort of goes funny. So that's effectively what this sort of thing that we think here is effectively the kind of development that occurs. So remember, so the thing was initially horizontal, and you start seeing two vortices, the transverse being sort of pulled on either side by the other guys. Okay, so we can look at this in great detail. Yeah. Okay, let me actually go maybe skip this one completely for the. Okay. Sorry. Okay. Yeah, it's not. You're showing real quick what I wanted to show, but let me do it. Yeah. Okay. So that's the one I want to see. Okay. So I guess sort of the most well, I mean, the cleanest thing, in relation to what I was showing before about this sort of a cascade mechanism we observed in this particular work. So that was done at a high enough Reynolds number of 6,000. So I guess the last slide I was showing was that so you start with filaments like this, and you effectively pull these sort of vortices which are perpendicular to the main one 2 by 2. So that's what we call secondary filaments, right? So you add something, and you start generating something. And by now you may have already you might see already where I'm going, right? So I was after this cascading mechanism whereby one per filament was going to something else of the same topology. How about that? So I guess that's what I'm trying to sell you here. So here are my secondary filaments. So there is a like this, and went like that. So of course, you see there are lots of degrees, and sort of the evolution, and it sort of gives something that charitably looks like a tertiary filament. Things I started like this, and went like this, and it's sort of the third layer of the filament that goes like this. Of course, the catch being that by that time, the solution is somewhat messy. There are lots of junk being left behind, but at least it sort of looks very plausible that there is some tertiary filaments going on here. And that okay. That we had, I was showing experimentally, we also had it numerically. But let me sort of show you it from a different side. So what I will be illustrating here is, okay, so that one will be from numeric. So I will look at dissipation, the epsilon, and I will sort of look at what the filaments look like. Right? So initially, if the filaments are very laminar and there's nothing over that, you go to see that you have it in the textbooks. And so let's just move try to recapitulate it now. So that instability that I was showing you is happening at about that time, where the dissipation hasn't grown right now. In fact, it's gone down because there is a capacity, and nothing of substance has happened yet. And then comes this secondary filaments generation, and so you start already forming small scale, and the dissipation grows, and if you sort of go even further, where you have these tertiary filaments, effectively you hit the dissipation, and amusingly, you have a spectrum of the solution that begins to come over i.e. So that's my spectrum compensated by phase by third, and it's not exactly fantastic, much better things, but it's still not so bad. And then afterwards, the solution just, well, after the peak, well, then it's going to just have some sort of turbulence, dies and returns to a laminar thing. That's some sort of things that has been looked at in great detail, the decay of a turbulence solution. Okay, so that's that. Okay, yeah, so that's right. So it's another pretty illustration. Yeah, so that one is very unique. So I'm going to show here the dissipation on the spectrum multiplied by the K2 factor. Right. So initially, of course, I'm sorry that I have to say here on my solution there's nothing that looks any close to turbulence. Then let me play it. So that's the beginning, and then whoosh up, and that's how the solution evolves, and the things dies, and so this Komogorov thing sort of starts decaying accordingly. Okay. No, it could be right, but that's okay. So the price is an off number. So we can put this up. Okay. So my impression with that is this one is probably this sort of saturated level. So what's going to happen is that the remote will start from further down. So I think that's not this calculation which I've done. It's another calculation which we can we show that one data is one, so which is the same, which is the same maximum height. So the amplification will be this divided by that. Right. Okay. So yeah. So that one's a little bit folkloric. Okay. So and that I will not. I will not dwell on because I don't have much time. Okay. Yeah. So okay. I'll just put up that one. So we put a couple of words about that one. So the question is whether. So what we have. What I try to show is some mechanism which sort of generates some sort of a smaller and smaller scales on the, so there's this notion of energy transfer and so on and so forth, or generation of small scales. So here is some sort of a, we actually crossing path with this Japanese group, who effectively has been thinking about the flow as some sort of generating some sort of a coarse grain vortices at the scale, and sort of at some sort of a higher K, some coarse grain at the smaller scale, using sort of these centers, which sort of plausibly look like it. I wouldn't put my head on the block about the pictures and whether that actually leads to proper energy transfer. It's certainly a way of generating some strong, enhancing vorticity. Whether that's sufficient to generate energy transfer is a different story. And so these are these slides which I'm sort of going very quickly through. And so now I'm on time. So having sort of so okay, so here are a number of things that I've explained to you. Yeah, so there is this sort of a long-lasting search for large gradients. So so we have here some mechanism whereby there could be some sort of iterative cascade which are generating smaller and smaller scales. Which certainly looks enticing for in the experiments I've showed you. How did that work in real turbulence? How much of it works as a core of turbulence? Was the two sort of a few slides that I sort of flew over, which would perfectly fit in the sort of things that oops, I'm not sure, but not for lack of time. But we can certainly discuss that further. Would be great fun. With that, I'll thank you very much. Steve. Yes, please. Yes. I guess what I'm trying to do is what I've been trying to do is sort of see where there is a different functionality in the reduction, I can tell you at some point you have this idea of cascade. Does it have the possibility to transfer I mean, I guess you go part of it and some ultimately after any kind of but I mean, before this, you know, it can go through to the state of the text. That's very fast. I think, you know, well, if you look at the simulation further, ultimately, you see that then you may ask, is it the end of the process? You know, I think it may just be, so, or the question would be, when does it want to stop? Because these vortices of fun, again, turbulence, they are not exactly intense. But you know, I think it's probably, I would interpret it by saying that you know, there's sort of a couple of thousand so if you're above 4,000, the thing would be crazy. If you're below a few thousand, it will not be very much. So for me, that would be, you know, what typically say that as the specific scale, you have to do multiple ones into nothing, between all the constant. And you know, I would sort of say that as long as a vortex has a Reynolds number of 2,000 or more, it has a potential of being banned. And you know, until it doesn't go any further. Which, you know, to me, I would sort of I would sort of be going to connect that with some other observation. But you know, I don't. I think they can sort of put you pretty far down. Well, I guess because you know the sort of quite conundrum I have when we're doing intermittency is that we sort of get more and more intense. So you know, in other words, so as the thing sort of breaks up more and more and more, somehow you get it goes further. It doesn't stop before. So I would just expect that the question is, you know, what sort of makes them sort of go further and further. But I'm a bit. I think I'm a bit fuzzy here. We should try to discuss.
I guess I have a question. When you approach, you tell me that since you have certain properties in the activity with this kind of instability, it's very remote. Can you say something about those kind of local transfer rates, those different
So that now, so far, you know, so you know, this line is so that way, so we're trying to see what royalty transfer occurring in this and you know, so and I think so here we are sort of fantastic. So the first one, if you look at the solution we're talking about, I'd say yes, it works that. So, you know, transfer is occurring vortices. We try to visualize what transfer in the physical space was, and you know, there's a motion that it's colocalized. So that one is good. On the other hand, sort of look at some sort of a more very smooth turbulence investment. So, you know, that's the sort of thing that I think quite much more understood. So, again, it's, you know, there are also all these vortices, because the very intense ones are not, whereas sure also you do that. So, you know, there is some sort of force going. Nonetheless, again, for the reason I'm showing, if you do the energy transfer, you get what over the course of the week, I think we have next and then they will Okay, so this is the second part of the question. You know, I think it's all the same. So yeah, ultimately that thing can start, can go. So let's ignore the first part of the question. I'll take that. But to the first part of the question, so well, you develop lots of jumps, you know, who knows what it does. Let's ignore that one. There's no but then, so of course, you're saying, well, you know, as I'm going into successive levels, then of course I'm using Reynolds. And ultimately, yes, Reynolds will be such that these things will not be unstable because they will be defined. And you know, you look at my first image, the first limit transparency of the Reynolds will 1000. It's an instability. So there is this sort of potential instability provided Reynolds one. So Blazes gain a few times, you know, each time you sort of lose in and at some point. That's it. So you know, yes, ultimately it's not even for Reynolds, not for maybe it's who knows what can happen. The other one, yes. Please notice that you know, I sort of send you this little quick message saying that instability needs not be stable. Some cascade needs not be stable. I guess that's effectively what we were going to happen. Right? So you know, this instability starts in an ideal world, it could go forever, but given the level of jump generated. So you know, that yes, that's you know, we saw one very well to try to yes, so we ever see something more unless we do something very special. No, it's yeah,
because